Hello, this video is entitled Additional Topics in Probability and Counting, 3.4 section in the Larson book. So let's talk about the first type of counting thing we're going to use here. It's called a factorial. This is all part of a branch of math called combinatorics, counting how many ways certain things can occur. And this is the most basic type of one to use. I'll give you an example. Well, we'll see some examples of this, but factorial. It's some calculators use X, but I'm sure it's got the exclamation mark after it. So, for example, n factorial means you start with a number n and multiply n times n minus 1, n minus 2, all the way down to 1. So, for example, here 4 factorial is 4 times 3 times 2 times 1, with 0 factorial having to be 1, and 1 factorial is also 1. I don't think we need this bottom one, but 1. But anyway, you don't have to know that in the sense because you can just put it in the calculator. And there's a big, long explanation why it has to be 1, but because actually there's some stuff where you do division and it better be 1 because you can't divide by 0. So, but that's not. There's actually a better reason than that. But here's in the calculator, super simple. But what you have to do here is you have to put the number first. I'll just do just a different one. There's 4 factorial, but I'll do like 6 factorial. You put the number in, you go math, PRB for probability, and there it is, number 4. So there you go. It multiplied 6 times 5 times 4 times 3 times 2 times 1 right there in a jiffy. But one of the things this factorial does is it counts the number of ways you can arrange a certain number of items in the same number of positions. And these numbers can get really, really large in a hurry. Like suppose that you took 10 people and you had 10 chairs. And you want to know how many, so the first, everybody's sitting down, and then that's one ordering. And then when people move around, that's a different ordering. So in other words, basically then how many ways could you sit 10 people in 10 chairs with every possible order would be 10 factorial. So you go 10 math, PRB, enter. So yeah, imagine if you're trying to keep a list of all those. Well, you wouldn't obviously, but if you had to keep a list of those, you'd be getting 3,628,800 ways that 10 people can sit in 10 chairs. It doesn't seem like it'd be near that many, but it is. Yeah, these can get really rude in a hurry. In fact, you could take, now I wouldn't suggest, unless you just felt like, had time to kill and wanted to do it. But for example, for this one, you could use letters like A, B, C, D, and you could put them in every possible arrangement of A, B, C, D, and you need to end up with 24 of them. I guess that would be kind of frustrating if you tried that and you got 23 and you couldn't figure out which one was missing. But yeah, there'd be 24 different ways to list that out. So here I'm mentioning that you put the number in before. So the number first, then the math, PRB, factorial that we just did. In Excel, you can do it there too, whatever's convenient. You just equal FACT and you put your number right in there and that spits it right out. So either way is good. Okay. So this is what I was just kind of mentioning. It's called a permutation. Now we're going to talk about if it's arranged in a different. If it's factorial, if it's exactly like 5 things in 5 orders, but we may be doing things where there's 10 things to choose from, and we're choosing 5 out of 10. That'll be a different calculation. But a permutation is a set of distinct objects, arrangement of the objects in specific order without repetition. There's no repeats. But the key on this is the order. The word distinct means the order matters. And we're going to talk about later when the order doesn't matter. It's a different type of thing. But permutation means the order matters. So like I was talking about, if you're taking A, B, C, D and rearranging every one of them would be a different order. In other words, A, B, C, D would be different than D, B, C, A. In other words, if you're talking about a permutation, every arrangement is different. All right. So fortunately, the calculation part of this is going to be easy. So this is the theorem of if you're taking, and that just ends up being factorial anyway, if you do this permutation formula, which I'll show you in the calculator. But if it's the same number like this says, yeah, you see, like, so the permutation of 7 items arranged 7 ways is just 7 factorial. But when it's different numbers, we'll see the way to do that. So like this says, how many ways can 5 paintings be arranged on the wall? It would just be 5 factorial. So if you had 5 paintings and you're trying to decide which arrangement you like the best, you've got 120 choices to pick out of which one you like. And the next one says, how many ways can a batting lineup of 9 players on a baseball team be arranged? It'd be 9 factorial. I'm not, since we're going to be, doing homework problems, I'm not going to worry about retyping these in right now, because like I said, you'll see real-time examples coming up. But anyway, so there they are, both calculated, and there's Excel. So 9 factorial, that means there's 362,880 ways you can arrange the order of 9 players in the batting lineup. That's a lot, isn't it? Now, the definition of permutation of n objects taken r out of time. Okay, you can kind of skip all this formula business because you're either going to be using the calculator or Excel, so we don't have to worry about that. But let's just talk about, how we look at problems and we know if it's going to be a permutation or that sort of thing, especially once we learn the next one called combination. Let's see. Well, I guess I have the work down here, and I may put these. I may put these in the calculator. In a horse race, how many different finishes among the first 3 places are possible if 10 horses are running? So, yeah, and the order matters in a horse race. In other words, obviously. So let's say, maybe you have the right 3 horses, but if you don't have them in order, you're not going to win. That's called a trifecta. If you're betting, so in other words, let's say you bet on horse 2 to come in first, horse 5 to come in second, and number 7 to come in third, and they come in 5 is first, 7 is second, and 2 is third. It's the right 3 horses, but the order mattered. You don't win because you had the right 3 horses, but you also didn't have the right 3 positions. So that's a permutation. It'd be permutation of 10, choosing 3 out of those 10. So in the calculator, you do this as 10, the first number, PRB, NPR, the second one. We'll be using NCR here shortly. NPR, 3, enter, and you see there's your answer, 720 right there. So there's 720 different ways for those 3 to be chosen, to choose 3 out of the 10. All the different orderings of the 3, in other words, not just, if you just take any 3 horses, like say horse 1, 2, 3, there'd be 6 orders. 1, 2, 3, 3, 2, 1, 2, 3, 1, so forth, so on. This means, this covers 720 ways to cover all possible top 3 finishes. In Excel, the function is called, let's come over here somewhere. I don't need a new spreadsheet necessarily here, just for this. Permute, and you'll see it in the notes there, but permute. Now, unlike the calculator where you got to put the number in before the function, this one you put it in there. You put the larger number first. Of course, they could both be the same number, but They could be the same, but it's never a smaller number than a larger number. Permute 10-3, there it is, 720. I think either of those are fine, I think. So as far as either works well without too much too much problem. What I have here is the older calculators like TI-83s and stuff. It shows it like this, but the newer ones, what did mine? Oh, mine's okay. I guess I don't have this one. Whatever here, I have another computer with a calculator on it. It has the newer operating system, and all that's going to do is it's going to show it with these subscripts like this. It's going to look like that. You'd enter the same commands, but it makes it look fancy like this because that's usually the way the permutation formula is. They have the subscripts there or whatever, so there's no real difference. It's just a fancier way to present it. In a long-distance foot race, how many different finishes among the first 5 places are possible if 50 people are running, excluding ties? Okay, in a race, order would matter, obviously. So how many ways can you get 5 different finishers in the top 5 out of 50? So I won't retype this one, but it's the same thing. So it's 50, NPR 5. It's a big old number. Well, out of 50 people, you'd expect this to be a lot, 254 million. And then in Excel, it's easy enough just to do, equals permute 50, 5. There they are. They match. That's always good. This is example 5. How many ways can a 3-person subcommittee be selected from a committee of 7 people? Actually, I need to edit this. All right, so I had to edit out part of that problem because the bottom part's here, what we're trying to do. How many ways can a president, vice president, and secretary be chosen from a committee of 7 people? All right, we're choosing 3 people out of 7, but we're choosing 3 in such a way that because they have titles, that the order of them matters. So if you choose 3 people, and they each have different titles, then the order that they're in matters. So that's what makes this a permutation. So it's 7 people choosing 3, and that would be this last calculation right here. 7 NPR 3 is 210. So the order matters. And then permute 7-3 is 210. Now we'll show you a different, similar kind of problem here in a minute which is the next thing we're talking about right now. Is called combination. A combination of n objects taken r at a time. So you're choosing r out of n, but this means, okay, both of them are no repeats or anything. You can't have repeats, but the order you choose them in does not matter. And you can skip the formula part of this. So let me just kind of refer back to one of the other examples, like the horse thing, for example. Let's say, well, it doesn't have to be a horse race, but let's just say that you have a horse farm, you're going to purchase 3 horses, and let's say there's 10 horses to choose from, and you're going to pick 3. And this is not where the order of the position, not like a race, where first, second, third. It's just, if you pick 3 horses, the order of them, that doesn't matter that you pick them. It's just how many ways could you just select 3 out of the 10 that you're taking home with you to your horse farm. So that would actually be what's called a combination. And I'll just put that in the calculator and I'll put that in Excel. Of course, we'll see some other examples. So in that case, if there's 10 horses, choose 3 to take home to your horse farm. You go 10, math, PRB, the one below it, number 3, NCR, choose 3. So there's 120 ways that you can choose just the 3 horses without regard to order or ranking. In Excel, the command is, I guess I didn't, I probably should have put, I'll copy this right here over there. So I mean, this was already in the notes, so it doesn't really matter that much, but yeah. but this one's not in the notes, so I'll put this in here. So I'll put it's combin for combination. Permute for permutation. Oh, 10, 10, 3. Oh, okay. Let me cut and paste this over to here. Copy this here to here. And there's the 120 for the combination. Yeah, permutation will always have more than combination, because permutation is not only are you taking the 3 items, you're counting the arrangement among the 3 items. Here, you pull out 3 horses, we don't have to count every possible order you took the horse. All right, so back to this. So you can kind of skip all this formula stuff here, because you'll just be using either the NCR in the calculator or the combin. Committee of 12 people, similar to what we did, except Part B will be different though. How many ways can we choose a chairperson, vice chairperson, secretary, and treasurer, assuming that one person can't hold more than one position? So it's a little bit different than the one I did before. There were only 3 positions. Here there are 4 positions. Chairperson, vice chair, secretary, treasurer. 4 positions. But the order matters, because they all have different titles. They're distinct positions. So that would be a permutation. Now Part B says, from the same 12 people, we just want to choose a subcommittee of 4 people. And notice it says nothing amongst those 4 people about how they're ranked or titled. Hey, we're just choosing 4 people out of 12 to be on this committee, and order does not matter. So if order does not matter, or distinct positions do not matter, that's what makes it a combination. So it'd be 12, choose 4. And that, you see, it's a much smaller number, 495. Wonderful. So here it's mentioning, okay, both of these share, neither one of them allow repeats. But in permutation, order is vital. Combination, order is irrelevant. Okay. Card problems. Now, somebody could possibly reword it and come up with some way to make it be permutations, but in our world, a card problem is going to be a combination. Just take that for granted. We're not going to do anything too creative here. Now we're going to be looking at 2 different situations multiplied together. And you have to use combinations, or sometimes in other situations they could be permutation. Like you'll see that the next problem will be an example of what I'm talking about. This is a more sophisticated version of the fundamental counting principle is what I'm getting at, that we learned earlier in another section. How many 5-card hands can we have 3 hearts and 2 spades? So what we're looking at here is there's 13 hearts, and we want to choose 3 out of the 13 hearts, and there's 13 spades, and we want to choose 2 spades. So it's going to be in order would not matter for the cards. 13, choose 3. I just did it all in one step. I didn't worry about getting the numbers individually. I just did it in one step. 13, choose 3, times 13, choose 2, combination, choose. And here in Excel, it would equal combin 13.3 times combin 13.2, and you see both answers are 22,308. Now this example, I was talking about earlier, we had that one example from the fundamental counting principle. That always meant you were choosing one item, so you didn't have to use combinations. That was one where I think it was you had to choose a dress, a purse, shoes, and something else, and you just multiplied the numbers together. This is a little bit different. You have to just use them. You're still multiplying, but you're having to use them as combinations. So a catering service has 8 appetizers, 10 main courses, and 7 desserts. A banquet committee selects 3 appetizers out of the 8, 4 main courses out of the 10, 2 no big deal, but that bugs me because desserts is spelled correctly here. What I have is deserts. Deserts. But anyway, yeah, I had desserts right there, but it's wrong there. All right, fixed it. A dessert versus a desert. 2 desserts out of 7 desserts. So they're combinations all multiplied together. 8, choose 3. 10, choose 4. 7, choose 2. I didn't show you. I didn't do it in the calculator. I guess I could real quick. Oh, there it is down there. Oh, this calculator screen has. I guess I could. Is it? Maybe I could snip it out of there and make some room for it up here. I'll pause for a minute. All right, now I brought the calculator part up here so we can see them both in the same problem. So the order doesn't matter. You're just choosing 3 of them. They're not specific order. So there are the 3 combins in the calculator multiplied together. And here it is, 8 NCR3. But like I said, yours will look probably fancier in the calculator. 10 NCR4 times 7 NCR2. It'll put those little subscripts in there like I was showing you. Same thing it did up here for the, where was it? Yeah, the little subscripts like that. It'll do the same thing for the C NCR also in the newer operating system. That's okay. That's not critical. Now the next question. 3 departments, 12, 15, and 18 members each. Each department selects a delegate and an alternate to represent the department at a conference. How many ways can this be done? All right, delegate and an alternate. That's 2 positions. But the fact that they are named and specifically named positions means the order would matter. It'd be a permutation. Because whoever's being the delegate is different than being the alternate. So these would be 3 permutations multiplied together. So it'd be permute 12-2 from the first group times permute 15-2 from the second times permute 18-2, and you get this 8 million something number here. And there it is in the calculator, all multiplied together in one step. So 12 permutation 2, 15 permute 2, 18 permutation 2. Then there it is written out, and there you go. Jury pool, 12 women, 12 men. Find the number of ways to select 8 women and 4 men. Order would not matter at all here. Looks like I didn't put this one in the calculator, but I'm not going to worry about it. I'm just going to leave the combin in there. Okay, the next one will have the calculator, so we'll do all right without the calculator, I think. So 8 out of 12, combination, order doesn't matter. Okay, typo. All right, I fixed the typo. It should have been 11 men. I decided, I could have changed it to the numbers to 12, but it was easier to change that to 11. So there's 11 men, choose 4 men. So 11, choose 4, and there everything matches here. So it's 11, choose 4. So it was easy just to fix that. So multiply those 2 together, and there we have it. "30 graphing calculators, 6 that are defective. 4 calculators are selected for a local high school. How many selections can be made?" So even though it says there's 6 are defective, we don't worry about that just yet. There's 30 total, and we're selecting 4 total. So how many, and order wouldn't matter. So 30, choose 4. Now the next one says, how many will contain no defective calculators? So we're choosing 4, but we're discarding the defectives. So basically, if you have 30 calculators, 6 are defective, you're left with 24. So we're asking, how many ways can you choose 4 calculators out of the 24 good calculators? So suppose maybe, they were checked. The first scenario, they weren't checked. They were just chosen, whatever, at random. But now we've reduced them down to the good ones. So it's 24, choose 4. So that'll be that answer, and there it is. combination answer. Wonderful. We can also find probabilities doing this kind of stuff. What's the probability of some of these events? And the difference is the numerator, you'll still be multiplying combinations together, but you'll be dividing by the total number of choices. So here is basically that same problem we had before. This one was saying how many ways can you choose, just how many ways can you get that different numbering of 8 women and 4 men. So this example 12 then says what's the probability of selecting 8 women and 4 men. So the number of ways to select the 8 women and 4 men is exactly the same. That's going to be your numerator. But you'll divide. So when you divide by the sample space, that just means the total number chosen out of the total number. This case, you break the women and the men down, in the numerator as far as the individual events. The denominator would just be, hey, you've got 23 people, 12 women and 11 men, and you're choosing 12 people. So we're saying out of choosing 12 people out of 23, based on that women and men breakdown, how many ways what's the probability that you end up with 8 women and 4 men? So that's how you choose. So it's 12, choose 8, times 11, choose 4, divided by 23, choose 12. And you see I did it in the calculator there, so multiplied them, then I divided, and you do it straight up in the combin. It'll combin times, and then divide by that combin, and 0.121 either way. I'm sure we'll see this in a homework problem also. Suppose we have a lottery number with 54 numbers and we select 6 numbers without regard to order. What is the probability of selecting the correct numbers on any one ticket? All right, so you're looking at choosing 6 out of 6. So you're saying there's 6 correct tickets. How many ways can we get 6 out of that 6? And then 0 out of the remaining 48 incorrect ones. So 6 out of 6 good ones, 0 out of 48. Notice these numbers add up. Let me mention, you're multiplying mathematically, but let me scroll back up to the woman, you see this jury thing. So you're multiplying, but notice that's another way you can tell. So 12 plus 11 gives you that 23, and then 8 plus 4 gives you 12. So that's how you can sort of check your numbers before you do the multiplying and dividing. So the total number of choices of way you can get 6 numbers out of 54 would just be 54 choose 6. That's your entire sample space of how many ways you can get 6 numbers. And then so it's 6 out of 6. You see, so 6 plus 48 makes 54. 6 plus 0 makes 6. That's scientific notation, which I don't know if I'll have anything that comes up like that on a test. But scientific notation just means that you move the decimal over to the left 8 times, which puts 7 zeros in front of it. And you see it also does it in scientific notation. The calculator probably would. I didn't put it in the calculator. It probably, because the number's so small, I'm betting it would show scientific notation. I'll put it in there real quick and then leave it in the notes. But it kind of doesn't want to show, if it's too many zeros to show, it won't show it. While I'm typing that in, so you can look and see, that's why it's so hard to win probabilities and stuff, because that's an extremely, extremely low chance you're going to do that. So times 48 NCR 0 divided by 54 NCR 6 let me do this. If I go, yeah, the problem is I can't get it to display Yeah, you can see me typing it in there, but I can't get it to show all on the screen. So I think I'll just snip out the punchline here that at least has the answer, and then you could probably then see how that arrow means it's, it carries over and it's not showing the rest of it. But the fact that I matched the Excel answer means I have the numbers in there properly. So we see the arrow on the right means, oh, okay, that's where the choose 0 would be, and then divide by the 54, choose 6. So that will stop the lecture, and let's pop over to let's see what we can do on the homework. So I usually skip some of the more basic ones here and just look for more. Okay, that's just simple calculation. I certainly want to do a probability or so. Okay, yeah, these are just straight up calculations. It's not even asking you to. Here we go. All right. Permutations, combinations, or neither. Number of ways, 13 ways can line up in a row for concert tickets. It's got to be a permutation because the order of the line, people in line. Yeah, I may leave it. Okay, let's see. I'll leave this one. This Love and Video Games. How many ways can you arrange the game side by side on a shelf? So it's just those 11 games. You can do it one of two ways. I'll show you. It's just going to be 11 factorial is going to be the answer. But watch this. So if you do permute, I can do 11. Yeah, see, when it's the permute and they're the same number, it ends up being the same. But obviously, if it's permute 10, choose 3 or something, that's not going to be the same thing. But when you're choosing 11 out of 11, where the order matters, then it's just the same as factorial. And I want to go 11, just so you can see this. But obviously, you can just use the permute. Permute 11 is going to be the same number. There you go. 399-16800. Oh, I guess I could be polite of me, I guess, to put it in Excel here somewhere. Yeah, let's do it right here. So permute 11. There we go. So that'll certainly work. Wonderful. And let's see. Like I said, we'll probably gets a little more interesting here. Okay, president, vice president, secretary, treasurer. Okay, that's in the notes. That's going to be a permutation because the order is going to matter. Oh, I'll do this one real quick. 5 subjects are selected from 45 subjects. No order. Order doesn't matter. So calculator would be 45 combination NCR. So let's try 122-1759. Fantastic. And I'll put it back over in the spreadsheet just to show you. It was 45. Oh, okay, right there. Okay, well, 45, choose 5. And like I say, you'll see it when I hit that. There we go. There it is. Comben 45, 5. So I don't know. It's whatever you like the best to do this. 12 horses, 3 horses, finish first, second, and third. Okay, that's just going to be a permutation. This one could be interesting. Oh, okay, there we go. So we got to read this carefully on this one. President, Vice President, Secretary, Treasurer, that's going to be a permutation, a full pool of 16 candidates. 9 of those are members from the debate team. So what is the probability that all the officers are filled by the debate team? So that means we're looking at 4. So we're choosing, the sample space will be 16, choose 4. 4 offices. Now the numerator is going to be, and I'll just put this in, like I said, I can put it in the calculator, I can put it in Excel, I can do both. It doesn't take long to do both. So I've got 9 NPR four times, that means there's 7 that aren't in the debate club. But we want none of those. So 0 out of the remaining 7. Then we divide by 16, choose 4, because it's 4 out of all 16 is your sample space. Three decimal places, 0.069. Hopefully this will be right. Fantastic. I can pop it. Oh, okay, we got more. But I could pop that first one in Excel real quick here. It was 9, choose 4. Permute. 7, choose 0. Divided by permute. $16, choose 4. Oh, stretch that out so you can see it. There you go. So there it is in Excel. Either way, works beautifully. Love it. Now let's see what it's trying to trick us there in the next one. No offices filled by the debate team members. And I think I'll just, to save a little time here, hope you won't be upset with me, but I'll just do the Excel and not the calculator. But I think when you see the Excel, you can figure out the calculator. So this is going to be just, you're basically saying on this one, and you'll see it when it comes out. 0 out of the 9, but all 4 are coming from the ones that, the 7 that aren't the debate club. So 0 out of the 9 debate people, but the 4 are coming, so that would be none from the debate club. So 0, 1, 9, if it wants 3 decimal places. Nope. Love it. I guess this is the last one, so I'll just do this one. Anyway, so similar kind of problem to the last one, I think. 28 workers, so there's more things here. 19 on second shift, 12 on the third shift. I'm probably going to do Excel again just to save time. But I don't feel guilty because I've shown you the calculator, so. But I'm not trying to place a preference on you there. I'm just showing you. Alrighty, 8 workers at random chose about the environment. So basically, 8 workers. Your sample space will be 8 out of, how many was that? To 28, 47, 59. So we'll be dividing by 59. Oh, and these are going to be, this will be a combination this time because there's no kind of order in this. They aren't ranked by position or anything. Exactly 4 third shift workers. Now this is a little tricky, so I'm glad I'm showing you this. I don't think I'll get this tricky on a test or whatever, but this will be helpful for you to be able to answer this question a little quicker. I thought maybe it would break it up by each individual shift, but what makes it tricky is we're saying 4 coming from the third shift, so you actually have to combine these other 2 together, and that means if we're choosing 8 workers, 4 are coming from the first 2 shifts combined. So watch what I do here, which has 47 workers. Well, a little sneaky there, but no, we're going to be all right. Combin. 47, choose 4. Meaning 4 workers are coming, out of the first 2 shifts combined. That's where the 47 is coming from. Times. Combin. I think it was 12. I'll double check that. I'll do it again. It was 12 in the third shift, I believe. Yes. But then the denominator is 59, choose 8. But like I was saying before in the notes, the lecture part, notice that, we are multiplying. Let's keep that in mind. This is multiplying, but I want to emphasize that, okay, the 47 plus the 12 does give you the 59 there on bottom, and then the 4 plus 4 gives you the 8 on the bottom. So that's good. If it's 3 decimals, that's going to be 040. Fantastic. Was that it? Oh, okay. Okay, I thought I was expecting a couple more parts to it or whatever. So, anyway. All right. Well, that's wonderful. Then that concludes this video on additional topics in probability and counting.